Dear students, for today we'll see what do we mean by Zener diode. We will say it's a construction, working, breakdown, a reverse breakdown specialty and applications. So let's start with the topic Zener diode. And in this presentation, we are going to see a definition of Zener diode, a construction of Zener diode, working principle of Zener diode, Avalanche and Zener, two types of breakdowns in reverse conditions, reverse VI characteristics, applications of Zener diode, specifications of Zener diode. So let's start with the definition. Now here, the two things which are important to remember about Zener diode is, it is same like your normal diode PN junction only, but here the P and N type of materials are very heavily doped. They are very heavily doped and it has a sharp breakdown voltage. It has a sharp breakdown voltage. Its speciality is to work in the reverse bias condition with a sharp breakdown voltage. Now, what does all these terms means? We'll see. So first we'll go with the definition of Zener diode. A special type of PN junction diode. So it is also a PN junction layer only. You can see P type of material which will be joined to N type of material, and then you will have a terminal here, you will have a terminal here. Same like your PN junction, anode and cathode. Okay, so same like your PN junction, but only thing here, it is heavily doped. This P type of material and this N type of material is heavily doped. That is, the addition of impurity to the pure semiconductor is very heavy. So you have a lot number of majority charge carriers in P and N type of regions. Okay. So here, as far as the definition is, a special type of PN junction diode that operates specially in reverse bias condition, reverse bias mode, more specifically in breakdown region, is known as Zener diode. The doping level of the Zener diode is somewhat higher than the normal PN junction diode, so that it can give a sharp breakdown voltage. This is very important when we see it's working in reverse bias condition. Then we'll show a symbol here. This is the symbol of Zener diode. So here you can see it is a two-terminal device. So the one terminal near the arrow is called as anode. This is your anode. And the other terminal near the bar is called as cathode. Okay, and you can show an arrow here. This is the arrow mark which gives the flow of conventional current, and the bar is somewhat little different than the ordinary PN junction or diode. That this difference is the bar is bent here and it is bent here. So, okay, so it takes a shape of Z, and this type of symbol of a diode is called a symbol of Zener diode. Then one more, you can see the symbol here. Again, we have shown anode as one terminal and cathode as one terminal. And in the second image, we have shown the real available Zener diode. So on this Zener diode, you can see this strip is there. This strip, whatever you see, this strip, the terminal which is near to that strip will be taken as cathode, and the terminal away from the strip will be taken as anode. Okay, so you can have the two terminals named as anode and cathode. Then about its symbol or description, we'll say its symbol is somewhat similar to the symbol of a normal diode. However, a small variation is seen in the symbol of a Zener diode, which is shown by the bends at the two ends of the vertical line. So we are speaking about these bends. When you draw the symbol of a diode, so this is the symbol of your normal PN junction diode. Now to this symbol, for this bar, if you have this bend here and this bend here, then this is the symbol of Zener diode. Then if you go to see the construction of Zener diode, then here both P and N type of materials are diffused, and then you get that PN junction. So here you can see you are showing a P type substrate. This is P type of material in which N type of material is diffused. Now diffusion has taken place, and here you are having the junction between P and N. This is the junction between P and N. So this is the junction between P and N. Okay, and the complete arrangement is metallized. So here you can see this metal, this is metallized, and this is also metallized. So metal contacts are given. The terminal which is connected to P-type semiconductor is called as anode here. This is taken as anode, and the terminal which is connected to N-type semiconductor is taken as cathode here, cathode. And there is a layer of SiO2 oxide layer, silicon dioxide layer. So here you can see silicon dioxide, and here also you can see silicon dioxide SiO2 layer. This is an insulator, and it is there to prevent the contamination of the junction. The junction should not get contaminated by anything. That is why some layer of SiO2 is placed over here and here. You can see in the arrangement. Okay, so this is the structure of Zener diode. So here about the structure or description, you can see here N and P substrate are diffused together. The junction region is covered with a layer of silicon dioxide, SiO2. At the same time, during a construction, the whole assembly is metallized. Everywhere metal is put wherever you want to make a contact with the terminal in order to generate anode and cathode connection. The layer of SiO2 helps to prevent contamination of the junction, thus is used in the construction of Zener diode. Then how does a Zener diode work? Okay, so it can work as a normal diode in forward bias and reverse bias conditions. But then what is the specialty? So let's see the description here. The operation of a Zener diode is like a normal diode in forward bias mode. That means a large majority current flows through the device when the forward potential is applied to it. However, a Zener shows variation from the normal diode in the aspect of its doping concentration. Doping concentration is important because the P and N type of material which you are having in Zener diode are heavily doped as compared to a normal diode. Zener diode is highly doped, that is heavily doped, thus its depletion width is very thin. So if you see the structure here, if you draw P and N type of junction, this is P and N type of junction. So here you can see this is P type of material, this is N type of material, this is your anode, and this is your cathode. Okay, this is cathode. So here the junction will have a very small layer, means very thin depletion width. So here the depletion width of the junction will be very thin. So here you can see it will be very thin depletion layer, because it is heavily doped. You have a thin depletion layer as compared to the normal diode. Okay, due to this, more current flows through a Zener diode as compared to a normal PN junction diode. It specifically acts in the breakdown region in the reverse bias condition. A Zener diode shows Zener breakdown approach. Okay, so the Zener breakdown approach is a specialty of Zener diode. Its operation in reverse bias condition is a specialty of this device, and that makes it a very applicable device, especially in the applications like voltage regulators. So here we will go to see then the reverse breakdowns which take place in PN junctions. So in PN junctions, normally the avalanche breakdown takes place, and in Zener type of diodes which are heavily doped, Zener breakdown takes place. So we can see here there are two types of reverse breakdowns occurring in the PN junction diodes, and they are number one avalanche breakdown and number two Zener breakdown. Now what is this breakdown? First we'll see, and then we'll go to see both the descriptions. So here if you have so here if you have a PN junction, okay, so if you have a PN junction, so here you can see P and N, okay. Then if you connect the P type of material to the negative battery terminal, and if you connect the N type of material to the positive battery terminal, so if you connect it like this, so it will be a reverse bias connection. Okay, so this is the reverse voltage applied. Okay, similar figure you can draw with the help of a diode also. So if you are having a diode symbol, say if you are having a diode symbol, then you can have a similar figure. You can have a negative terminal of the battery and positive terminal of the battery, and you can have it like this. So this diode can be your PN junction diode, or it can be a Zener diode. If it is a Zener diode, then you can show a symbol like this. Okay, so here with respect to PN junction, we will speak. Whenever you connect this negative battery terminal to the P-type semiconductor and positive battery terminal to the N-type semiconductor, the electrons present in N-type semiconductor will be attracted towards the positive terminal, and the holes present in the P-type semiconductor as majority charge carriers will be attracted towards the N-type terminal, and this depletion layer will be increased. This depletion layer will increase between P and N junction. Now, for the minority charge carriers which are there in P and N, in P electrons are minority charge carriers and in N holes are minority charge carriers. So for them, this arrangement of voltage will act as forward bias. So minority charge carriers, so electrons here and holes here. Very few number of electrons are there in P type, very few number of holes are there in N type, which are minority charge carriers, which are generated because of temperature. For them, this type of arrangement will be like a forward bias arrangement. Now, when you apply this voltage, and if you see the graph says that when you see the third quadrant graph for reverse bias condition, let the x-axis be voltage and the y-axis be current. This is the reverse voltage and reverse current. We see that till you increase the reverse voltage, till some time there is no flow of current, and at a stage comes when there is a more flow of current. Okay, so this voltage at which it happens is called as breakdown voltage. This is the breakdown voltage, and this is the breakdown region. Here you can see the breakdown region where the current is increasing drastically. Now this process of breakdown are of two types. One is the avalanche breakdown and one is Zener breakdown. In normal PN junction diodes, you can see avalanche breakdown, and in PN junctions which are heavily doped, you can see Zener breakdown. Okay. So first we'll see what do we mean by avalanche breakdown. So here avalanche breakdown is usually subjected to happen when the applied reverse bias voltage is high. As we already know that in reverse bias conditions, small minority current flows through a normal diode. When a high reverse bias voltage is applied to this device, the minority carriers experience acceleration, force. They experience a force and moves with high velocity. During its movement, minority carriers will dash or collide with the atoms and generate more number of free electrons. These free electrons further generate some more free electrons. Thus, there is a multiplication process of free electrons. Thus, a high electric current is generated due to this multiplicative action. Hence, we say high potential in reverse bias is required in case of avalanche breakdown. This high current is responsible for the permanent destruction of a normal diode, but an avalanche diode carefully manufactured to operate in the breakdown region withstand the high current flowing through it. So there is a limit for the high current which can flow in the reverse direction. So that is shown here. If you take the graph of the third quadrant, so if you take negative voltage, that is reverse voltage and reverse current, so you can see from zero, if you increase the applied voltage, the voltage across the diode is very going to increase, and as it increases at some stage at one level, there will be multiplication of minority carriers. There will be a large flow of minority carriers which will flow, and then there will be a breakdown region here. This will be called as a breakdown region, reverse breakdown region, and the voltage at which it happens is called as breakdown voltage. Okay, so this type of breakdown where you are going to generate the minority charge carriers, you are going to accelerate them. Okay, the minority charge carriers will be accelerated and they collide with other atoms and generate more free electrons. This type of process of generating more free electrons and then getting more electrons for minority charge carriers and then seeing the increase in current is called as avalanche breakdown. Then we'll go to see Zener breakdown mechanism. So here you can see this is a structure of Zener diode, and you can see the width of the depletion layer here is very, very small because of heavy doping. So this width is very small here. So you can see this width of the depletion layer is very small due to high doping concentrations, because the p-type material and n-type material are very highly doped. So this connection is a reverse bias connection where p-type is connected to negative terminal of the battery and n-type is connected to positive terminal of the battery. So the majority charge carriers, that is holes, will be attracted towards the n-type terminal and electrons will be attracted towards the p-type terminal. But for minority charge carriers which are there in p and n, in p the electrons here are minority charge carriers, okay, and in n the holes here are minority charge carriers. For them, this type of voltage arrangement will act as forward bias. For them, it will act as forward biasing. So that forward biasing effect will be there on the minority charge carriers of p and n junction. Okay, now because of this high doping, heavy doping, the narrow whatever depletion layer you have, this will build up its own electric field. This will build up a electric field which will create more covalent bonds breaking, and you get a lot number of free electrons, and thus the current goes on increasing. That happens in Zener breakdown. Okay, so let's see the description. Zener breakdown mechanism. This breakdown mechanism is noticed in diodes that are heavily doped. Due to the high concentration of impurities, the width of the depletion width is narrow. With the increase in the reverse potential, a strong electric field is generated by the depletion region. This is very important. This line is very important. With the increase in the reverse potential, that is the applied reverse voltage, a strong electric field is generated. A strong electric field is generated by the depletion region. This is a very, very important statement in Zener breakdown. Okay. Now this strong electric field, what it is going to do? As the reverse potential is increased, the electric field at the junction also increases. High electric field at the junction causes the covalent bonds to break. This will make the covalent bonds break, thereby generating more free electrons. This action generates more free electrons and hence their movement produces electric current through the device. This is the Zener breakdown. Thus, a small increase in reverse voltage will cause an immediate increase in the current through the device. The current flowing through the device shows its maximal increase up to the circuit permissible limit value. This reverse current will remain constant for a wide range of reverse potential. When a Zener diode operates in the breakdown region, it does not burn rapidly. Okay, this is a specialty of this diode. However, the reason for this is some external circuit is required in order to protect the device from the excess current. But it is used in this area only. Zener diode is used in this area where it goes under reverse breakdown, where the voltage remains constant but the current goes on increasing. This is specialty. The current can vary high and low, but the voltage remains constant. And this specialty of Zener diode makes it a very useful device for circuits like voltage regulators. Then we will see the VI characteristics for germanium and silicon diodes. So here you can see the breakdown for germanium is happening early and then silicon is happening late. So first we'll see what is the forward bias condition. So here you can see forward bias condition. So it is same like your conventional diode. If you start from 0, as you increase the forward voltage, the germanium will have a new voltage of 0.3 and silicon will have around 0.7, and then once that applied voltage crosses that new voltage, then the current goes on increasing. Even here if you see, if you cross the new voltage, the current will go on increasing. So this is the forward bias condition, which will be same like your PN junction ordinary diode. Okay, if you see the reverse conditions, okay, for germanium it is getting breakdown early, and for silicon it is getting breakdown little late. Okay, but in both the cases you can see the breakdown is sharp. The breakdown is sharp here. It is sharp. So here you can see if you have a breakdown like this, and this will be a sharp breakdown. This happens only in Zener type of breakdown, Zener breakdown, where the PN junction is heavily doped, and in normal PN junction this breakdown will be little blunted like this. Okay, so this type of sharp breakdown you can see in Zener diode. So here also you can see a sharp breakdown. Here also you can see a sharp breakdown. At that breakdown, the voltage will remain constant and only the current will vary from low to high. So the figure represents the curve of both silicon and germanium diodes. The forward characteristics of the Zener diode is similar to a normal diode, which is clearly seen in the figure above. In reverse bias condition, a small reverse current flows due to minority charge carriers on increasing the reverse voltage. Current increases. A point is reached when the junction gets destroyed and a sharp increase in current is noticed without any noticeable increase in the reverse potential. This voltage is known as Zener voltage. The current through the device is limited by making use of external resistance. Then we'll go to see what are the applications of Zener diode. The most and the main important application of Zener diode is in voltage regulation. So number one, in voltage regulation, regulating the voltage of a circuit is its ability to keep the output voltage fixed regardless of the variation in the input voltage or load current. Even if the input voltage main supply voltage varies, or even if the load current varies because of the load variation, in both the cases, Zener diode can help you to give a constant output voltage because of its speciality that in reverse breakdown, the voltage remains constant and current can be varied. Number two application is in switching operation. A Zener diode can be used for switching purpose because it shows an abrupt transition from low to high current. Due to its such switching characteristics, it is widely used in computer applications. So it can be used as an on-off switch. Number three, it can be used in meter protection. A Zener diode can protect a meter from the excessive voltage applied to it. Here also again, it is going to act as a voltage regulator. A parallel connection of Zener with the meter causes excess current to pass through the Zener rather than the meter, thereby protecting from severe damage. And number four, it can be used in clipping circuits. Zener can be used in clipping circuits where the peak of the applied input is clipped off. Usually, our clipping is done to protect the voltage sensitive devices from over voltages. So these were the few applications. Out of these four applications, the most important application is Zener diode as voltage regulator. Then we'll see some specifications of Zener diode. Some are commonly used specifications for Zener diodes are as follows. Number one, Zener or breakdown voltage. The Zener or the reverse breakdown voltage ranges from 2.4 volt to 200 volts. Sometimes it can go up to 1 kilovolt, while the maximum for the surface mounted device is 47 volt. Now the breakdown voltage, what we use in the lab for Zener, it can be either 6 volt or 12 volt. The 6 volt Zener will be named as FZ6. Okay, so if you take FZ6, it is a, if you take FZ6 Zener a diode, it is a diode which is having the reverse breakdown voltage of 6 volt. If you take FZ12, then it is a diode which is having a reverse breakdown of 12 volt. Okay, so these are diodes we will see in the lab. Then number two is a current IZ maximum. It is the maximum current at the rated Zener voltage VZ is equal to 200 microampere to 200 ampere. Then a current IZ minimum, it is the minimum value of the current required to the diode to break down. Then fourth is a power rating. It denotes the maximum power the Zener diode can dissipate. It is given by the product of the voltage of the diode and the current flowing through it. That is P is equal to V into I. Then fifth is our temperature stability. Our diodes around 5 volt have the best stability. Then sixth is voltage tolerance. It is having typical tolerance of plus minus 5%. Then seventh is Zener resistance RZ. It is the resistance of the Zener diode exhibitions. Okay. So whatever a Zener diode exhibits its resistance, it is called as Zener resistance. Thank you, students.